Algebraic properties of the scalar product. Welcome, everyone. Before we dive into today's lesson, let's take a moment to recap. In our previous sessions, we established the fundamental definition of the scalar product, which you might also hear referred to as the dot product of two vectors. Now, it is important to remember that while vectors are fundamentally different from real numbers, because they possess both magnitude and direction, you will find that the scalar product behaves in a remarkably similar way to the multiplication of real numbers. This similarity is what makes our work much more intuitive. In this subsection, we are going to explore the specific algebraic laws that govern the scalar product. Mastering these laws is essential, as they provide us with the necessary tools to simplify much more complex vector expressions that you will encounter later in your studies. Commutativity. Now that we have established what the scalar product actually is, let's look at its first major algebraic property, commutativity. When we say the scalar product is commutative, we mean that the order in which you multiply your two vectors simply does not matter. You will arrive at the exact same scalar value regardless. If you look at the mathematical expression on the screen, you'll see this written as vector A dot vector B equals vector B dot vector A. But you might be wondering, why is this true? To understand this, let's look at the geometric definition of the dot product. We know that the scalar product is defined as the magnitude of vector A multiplied by the magnitude of vector B, all multiplied by the cosine of theta, where theta is the angle between them. Because the magnitudes of these vectors and the cosine of the angle between them remain exactly the same no matter which vector you list first, the final result is identical. This is a very helpful property to keep in mind as we move on to more complex operations, like the distributive law, which we will cover in the next slide. Distributivity over addition. Now that we've seen how the order of vectors doesn't matter in the previous slide, let's move on to our next property, distributivity over addition. Essentially, this property tells us that the scalar product is distributive over vector addition. In simpler terms, this means we can distribute a single vector across a sum of other vectors, much like how you would distribute a number across parentheses in basic algebra. If you look at the mathematical expression on the screen, you'll see vector A dotted with the quantity vector B plus vector C is equal to vector A dotted with vector B plus vector A dotted with vector S vector C. To make this concept more concrete, let's look at a real-world application in physics, the concept of work done by a constant force. In physics, work is defined as the scalar product of a force vector, F, and a displacement vector, d. Imagine you are pushing a heavy box from point A to point B, which is a displacement of vector d, 1, and then you continue pushing it from point B to point C, which is a displacement of vector d2, all while applying the same constant force, vector F. The total work done is the force dotted with the total displacement. Mathematically, that is, total work equals vector F dotted with the quantity vector d1 plus vector d2. According to the distributive law we are discussing today, this is exactly the same as calculating the work done for each segment of the journey separately and then adding those results together. So, total work equals vector F dotted with vector d1 plus vector F dotted with vector d2. If you are solving a problem using this property, here is a step-by-step breakdown to follow. First, identify your vectors by determining the components of vector A, vector B, and vector C. Second, apply the law by expanding the expression into two separate dot products. Specifically, a dot B and a dot C. Third, calculate each dot product individually to get two separate scalar values. And finally, sum those two resulting scalars to find your final answer. This distributive property is a powerful tool that we will use alongside scalar multiplication in the next slide to simplify even more complex vector expressions. Scalar multiplication. You'll notice that the scalar product interacts linearly with scalar constants. In simpler terms, If you decide to scale one or even both of your vectors by a constant, which we will call lambda, the resulting scalar product will also be scaled by that exact same constant. If we look at the mathematical expression on the screen, you can see this written as lambda vector, a dotted with vector b, equals lambda times the quantity vector, a dotted with vector b, which is also equal to vector a dotted with lambda vector b. What this property is essentially telling us is that the order of operations regarding the constant doesn't matter. It doesn't matter whether you multiply the vector by the scalar before you perform the dot product, or if you simply multiply the final scalar result by that constant at the end. The outcome remains identical. To make this concrete, let's walk through an example breakdown. Suppose we are given that vector a dotted with vector b equals 5, and our goal is to find the value of 3 vector a dotted with vector b. First, we identify our scalar, which in this case, lambda, is 3. Next, we apply the property we just discussed, bringing the 3 outside of the dot product, so the expression becomes 3 times the quantity vector a dotted with vector b. Then, we substitute our known value into the expression, which gives us 3 times 5. Finally, after our calculation, we find that the result is 15. Now that we have covered how the scalar product handles commutativity and addition, let's move on to our fourth slide, which discusses scalar multiplication. This property is incredibly useful for simplifying expressions before you even begin your calculations. Now, let's take a moment to summarize everything we've learned in our key takeaways. Key takeaways. First, we have commutativity. As we saw in our second slide, the order of the vectors in a dot product is irrelevant. Mathematically, we express this as a dot b equals b dot a. Essentially, it doesn't matter which vector you list first. The resulting scalar value remains exactly the same. Second, let's look at distributivity. Building on our discussion about vector addition and the physics example of work done, remember that the dot product distributes over addition. In notation, this is a dot the quantity, b plus c, equals a dot b plus a dot c. This property is vital because it allows you to break down complex vector sums into simpler, individual dot products. Finally, we have scalar scaling. As we explored in the previous slide, the scalar product interacts linearly with constants. This means that if you multiply a vector by a constant lambda before performing the dot product, it is mathematically equivalent to simply multiplying the final scalar result by that same lambda. All right, let's take a moment to pause and recap everything we have covered in this lesson so far. This slide serves as a summary of the 3 fundamental algebraic properties of the scalar product that you need to master. Keep these 3 rules in mind, as they are the tools you will use to simplify almost any vector expression. Now, before we move on, I want to highlight a few common pitfalls where students often lose marks, so let's look at the next slide carefully. Common mistakes to avoid. First, be very careful not to confuse the dot product with the cross product. Throughout this lesson, we have seen that the scalar product is commutative, meaning, as we saw on slide 2, a dot b equals b dot a. However, it is a mistake to assume this applies to all vector operations. The vector, or cross, product is actually anti-commutative, which means a cross b equals negative b cross a. The order matters immensely when you are dealing with cross products. So always double-check which type of product you are working with before you start calculating. Second, watch out for result-type errors. It sounds simple, but it is a very frequent mistake to treat the result of a dot product as if it were another vector. I want you to remind yourself of the very name we are using, the scalar product. By definition, the result of a dot product is always a real number, or a scalar, and never a vector. If your final answer has direction components like I, j, or k, you know you've made an error. Finally, let's talk about incorrect distribution. When you are applying the distributive law we discussed on slide 3, specifically, a dot the sum of b and c, make sure you are actually performing the dot product operation. A common error is to distribute the vector a, but then forget to actually calculate the dot products, leaving your answer in a messy vector form. You must ensure that vector a is dotted with vector b, and then vector A is dotted with vector C. And finally, you sum those two resulting scalars together. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. We have just covered some very powerful algebraic properties, but as with any new mathematical tool, there are a few traps that students often fall into. Let's look at these common mistakes to ensure you can apply these laws with confidence. If you can avoid these 3 mistakes, you will have a much smoother time mastering vector algebra. Let's review everything one last time.